just like.
Okay, so yeah, as Noah said, this project is just basically about trying to take simulations, integrate those into assignments, and see what the factors are that we need to account for. And so we started with this set of heuristics, and this is just a partial list here, but we've got things like use the sim to mediate discussion, set up game-like situations, utilize eliminating cases, and a whole list of these things that, really we developed these based on kind of what we thought would be important at first. And then, as I started to design more assignments, we've been able to refine this. And in addition, we really felt like the set of heuristics wasn't in itself enough to sort of explain how to integrate the sim into the assignment. So we came up with this framework, and basically you see here, we have the features of the sim, and this is going to affect the environment. So what the students are doing, what they're working on, what their questions are, what the teacher even does. In addition, the features of the sim are going to influence how the assignment's written. So, like if the assignment if the sim has like a game-like thing in it, maybe you'll tailor the assignment to that, stuff like that. So then on the other aspect here is that the environment or situation is going to affect your assignment. So how you write the assignment, like for instance, if I have, if I want to have the students work on a homework problem, then obviously, that's going to be different than having them work on a tutorial. And at the same time, the assignment's going to influence the environment and sort of what the students are doing. So really, we feel like the heuristics are found. So the heuristics are implemented in these two areas. So you look at the features of the sim, you try to implement the heuristics to make the assignment. You also look at features of the environment, implement those heuristics to help create that assignment. So this is the study that I'm talking about today is the projectile motion homework problem in Class Mech and Math Methods 1. So this is kind of like the student's first upper division class, I guess you could call it. And so I held 2 homework help sessions, and I got about 5 students who showed up total. So basically, the question is about quadratic air drag. And so, you shoot a ball into the air, and you want to find like the velocity as a function of time, and how long it takes to get to the top, and stuff like that. So the problem starts out with math, and so the students are working on solving a differential equation, and then solving for the time it takes for the ball to reach the top. Okay, and then we move on to the sim, and we say like, okay, play with the sim and see how long it takes, or see what velocity you have to shoot the ball at to get it to hit the top in exactly 3 seconds. And then, compare how long it takes for the ball to go up compared to how long it takes for the ball to go down. And then there's also this sort of weird asymptotic behavior that, I don't even know if anyone knows that this happens, but there's a limiting case where, you can't get the ball to go up for an indefinite amount of time. There's a limit on that. So,
which, by the way, is a great thing to sort of consider. Here's a great comprehensive exam question. Compare T up with T down. How long does it take for the ball to reach its peak on the way up versus to come down? Common naive answer is, well, it's the same, silly, right? But that's without air. Okay.
Yep. So here's how the times broke out. So on Tuesday we had the students on. There were 2 students Tuesday, and they spent 1 hour and 45 minutes on part A, solving the differential equation.
Sorry, Danny, how were the students chosen?
It's totally random. Whoever wanted to show up.
I see. This is just open.
Volunteer.
Yep. There are about 50 students in the class. So, yeah. On Wednesday, same thing. These students were a little more on top of it, trying to move faster. I think they had some stuff that they had to get done afterwards. So they took an hour. this second part, solving for t-top, I mean, once you have the formula for v, it's pretty easy to just figure this out. And so here's the times on using the sim, and as you can see, it's like, 5 minutes, 10 minutes. It's not a lot of time spent using the sim. Okay, and so here's the problem. Don't try to read this, but so basically here's the old problem that I gave out last semester. So as you can see, all this green stuff is what I changed. And so here's the new semester. So most of it's the same, and I'll go into more details about what I changed, but I just wanted you to see like what the problem looked like.
But these colored parts are the parts that directly have students use the sim, really.
And this part right here, which didn't change. So yeah.
For the red, green colorblind in the group, you might pick different colors. I can't see the difference.
All right. Yeah, it comes up a little better on this screen, but. Okay, so I just want to go into more detail about the Tuesday environment. So we were in the chairs conference room on Tuesday. So there's the table in the chairs conference room. Okay, and we had 2 students. They were situated kind of like that. Okay. So Wednesday was different. We started with 3 students sitting like this, and what happened was basically.
One line on
What's that?
One died.
Yeah. One was really tired. But so these 2 were, we started like this, and these 2 were collaborating a lot. And they were doing the math, so they weren't using the sim yet. But this student was kind of left out, and so I suggested that they rearrange the tables, and so they ended up sitting like this at the end. And so what happened was, instead of these 2 students talking to each other, these 2 started talking to each other. This one started getting kind of left out, and he actually fell behind and never caught up. So here's some comparisons with what I changed, from last semester. So Part C basically says, so the old Part C says, the sim shows you the value of these things. Use your formula from Part B to figure out how long or what initial velocity you have to shoot the ball at to get it to reach the top in 3 seconds. And then it says, okay, now try it with the sim. Now find out, did it work? So I changed this, and I start with so Part C starts with, okay, by experimenting with the sim, what initial velocity makes the ball reach the top? So they haven't done any calculations yet. They're just supposed to play with the sim and basically figure this out experimentally. And then I say, okay, go back to the math and see if you get the same answer. So what were the responses? So one student, Ben, we'll call him, he read Part C and he immediately went to the sim, started playing right after he'd read it. Okay? And so on Wednesday, I want to give you a little audio here of what they, let's see. So this is from Wednesday.
Is this just using the sim?
I'm skipping to D just because that doesn't involve the sim.
Okay, fair
D is more. Or do we need to do it in order?
I prefer it.
Okay.
But can you tell me why you skipped it?
Why? Because then I would don't have to putz around as long.
Okay, so could everyone hear that, first of all?
Really?
Okay.
Did he just use the word putts?
Putts, yeah. So they wanted to move on to Part D and calculate first, and then go back to the sim and test it out. And so I asked them to play with the sim first, and they did. But he basically said he wanted to do that because he didn't want to putz around with the sim for so long.
The implication being that it was inefficient.
Yeah, right. He had other stuff to do. So he was going for efficiency. One other kind of interesting piece here is that when the students first start playing with the sim, they always want to shoot the ball at an angle. And, it was kind of weird to me at first because the whole problem so far has been about shooting the ball vertically. And, they read part C and they're like, they start shooting it and they're trying to figure out how long it takes to get to the top of the trajectory. Or they're trying to get the ball to reach the top of the trajectory at 3 seconds, but at an angle. So they're not actually doing what, I guess not maybe what they're supposed to, but what the problem's asking for.
But they're doing what we normally use cannons for.
Right. Right.
You're usually trying to shoot something else.
Well, yeah, I mean, when I first started playing with the sim, that's probably the first thing I did too. I don't think I thought, oh, I'm really interested about shooting it straight up. But,
Did they ever get to the straight up part?
yeah. I had to tell a couple students to, you're actually supposed to be shooting this straight up. And they're like, oh, yeah, I guess that was kind of implied in the problem. But they didn't, I had to tell them to do that. So here's the other part of the question. And so it says, let's look at another interesting feature. So shoot the ball up and then increase the initial speed by, double it, and then, increase it by 10, and then by 100. What's happening? And so I changed this question this semester to say, playing with the sim, write down the initial velocity that makes the ball reach the top at 4 seconds, then 5 seconds, then 6 seconds, and so on. The reason I chose to rewrite it this way was because I felt like this question was just too guided. We're telling them exactly what to do. Like, plug in, this value and then increase it and notice what's happening. This one, you could imagine rewriting this as a table. So, t equals 5 seconds, fill out this box for v0. So it's a different format.
And this is to get at the asymptotic behavior.
This is, right.
So one of these you can't answer. Like 7 seconds you can't answer.
No, 6 seconds you can't answer. So it's, and I'll get to video of them. Yeah.
So I did this because I was testing the board for Alicia, and I found that the sim couldn't give me like satisfactory answers, at least to the accuracy that I wanted. And I wondered if the students had that.
Oh, with finding out.
Right, finding the
How.
Do you have to zoom out to keep figuring out when it gets
Yeah,
to
and
the
you
top?
can't zoom into the top.
Right.
Yeah, so it's an estimate. It's like you kind of have to guess. Okay, so the response on this was, for the Tuesday group, so Ben just didn't even realize the asymptotic behavior. He read the question and he went and played with the sim, and he actually thought that he had found a time where he could get it to reach the top in 6 seconds. And so I think he had maybe just been watching the sim and not paying close enough attention. On the other hand, so going back to this video, so basically what I'm going to show you here is, so this is that same group of students, and they had already figured out how to get the ball to, or what velocity they needed to get the ball to reach the top in 4 seconds. And so now they're trying to do 5 seconds.
I guess mine is 2. And you're like 210s?
I'm at 220 now. Yeah, I think it's going to be close to 220.
Those tip marks are 1 second intervals, so that's how they know that it's the top.
Yeah, 225.
Wow.
370.
So they're satisfied that they got 5 seconds, now they're going for 6 seconds.
Jeez, yeah, you're right. I'm thinking close to over 400 at least.
I'm going 450 just because.
450 for fun. Yeah. No, more than that. Fuck it, 600. Jesus, it's more than that.
Wow. 7.
I'm going 775. The rate this shit's going.
Yeah, right. Wow.
Good God, it's still coming down. 900.
That's what I was like, screw it, 200.
Fuck this thing.
No?
I don't think it's possible.
It'll never stay up in the air for 6 seconds.
1500, there we go.
Okay, so that's the first part, and I'm going to skip ahead a little bit here, show you the rest.
That sounds just like I'm supposed to.
How, so they were about to go on to 1500. Was that the last thing they tried, or
Nope.
did they just keep going? And
They're going to keep going. Let's see, what do they start at? They're going to be around 4,000 or 8,000 right here.
10. Let's try 10 grand. One, two.
Wow. Are you still doing speed? Or not?
It's over 10 too. I would just go straight to 20.
No.
Did you guys get 35.666?
Yeah.
For the terminal velocity?
Yeah.
It comes down at 20. It's still coming down at 20,000.
Wow.
Just jump straight to 60,000. It's got to be less than that, right? I think your sim's broken, Danny. There can't possibly be that much difference between 5 and 6 seconds worth of hang time. I mean, I'm sitting here at 10. Nope, this is going to be 100,000 now, I think. Yeah.
What are you guys trying to do?
It's still coming down at 100,000.
Which question is this? Are you guys on? This is just going nuts, please.
F. It's just like take a bunch of data points and make a plot, basically.
I'm at 120,000.
Let's go to 500,000.
Seriously. Wait.
It's still coming down. I don't think it's possible. I'm going to say vertical asymptote.
Is it possible?
Here's a hint. Read the question again.
Well, I guess we noticed it asymptoting.
Yeah.
So I'm just going to put that.
So can you explain mathematically why?
Oh, probably.
Okay. So they finally figure out that it's an asymptote, and okay, so after that, I basically asked them, can you explain with your mathematics why that's the case? And so they started to do that, and they've actually made a plot of, we eventually made a plot of t to the top versus, v0, and it does this tan inverse thing where it's like an asymptote, and so I've got a little bit more here to play, and this is kind of about what their response overall was to
This is
Yeah, that makes sense. I like that. Cool.
so
so
that's like, would you have expected that?
No. I would have expected you could have gotten time to top for just about, any time you so
Right.
desired.
Right, like when you
Without air resistance, you could.
Right. Without air resistance, you absolutely could, but that's the point is...
Right. The concern is so large that it's like to dominate.
right.
So much so that it's a limiting factor.
right.
Yeah.
And I don't think there's any limiting factor on how high you can shoot it. I mean, you can always crank up that velocity, and it's going to cover more
ground, right? That's why
More vertical height, yeah.
Yeah, you have to just keep zooming out.
Mm-hmm.
But yeah, it's bizarre to me that it's like no matter how fast you shoot it.
Yeah.
So that's why you wanted us to dig around with a bunch of things.
Yeah.
Waste a bunch of time when I can be off doing a different lab write-up, right?
Yeah, but now we know this really well.
You should show up tomorrow and buy me a beer at Old Chicago. I'm there every Thursday.
So, I mean, that, yeah.
Well, it's easy to be like, oh, it's so funny they didn't figure that out. But if they're bringing their intuition of the world around them, you would find that you shoot it fast enough, it's never going to come. There's an escape velocity they could reach. I mean,
Well,
so it makes sense that they would be like, wait a minute, I know I can shoot it faster and get it to stay in the air because in reality they could.
yeah.
No, you can't.
You can save 6 seconds in the air, sure. Well,
Only if it
atmosphere
leaves the
things,
atmosphere.
you know,
If it's
Yeah,
in
right.
the atmosphere.
you can have to shoot with an escape velocity and it will never come back.
If you shoot it up with the escape velocity, it will get slowed down by the air. The
Sure.
escape velocity
But
is
you can
just
get it to
maximum.
stay 6 seconds before it reaches its peak. You can get it to take 6 seconds before it stops and starts coming back. You can have it go infinitely long before it stops and comes back.
Not with air resistance.
Well, air resistance stops though. I mean, that's in reality, we don't have this constant air resistance.
Well, in reality, it's going to burn up.
Well, but you see
So
that
the
their
fact that
intuition,
you
but you
can't
know
get
that we launch things out into space. You shoot it hard enough, it's going to go up.
No, that's not the way it
Well, no,
launches.
it's not how we launch things, but-
You don't fire things from into space with a cannon. You have a
No.
rocket with a continuous.
No, I understand.
Right,
But-
I think it's like the model in the best in is that there's constant atmosphere.
Right, constant gravity,
Right,
constant atmosphere.
Right, which is not.
Yeah, you can shoot it over the speed of light too. So.
Sorry.
I can see that would lead them to think that they can shoot it and
I don't know.
I don't know.
That's what they were thinking.
You bring up a good point, which is to say, all right, how does this jive with student intuitions, and are those intuitions reasonable and whatnot? So that's an interesting point here. Now, hard to know what it is that why students were sort of thinking this or not. But this didn't jive with their intuition, that's for sure.
Yeah.
But they left having better intuitions about it now.
Yeah,
At least that's what they stated.
right. So to just
A couple minutes.
to just go briefly over this, so the response was first the sim's broken, then they said, why did we waste time doing that? And if you heard at the end, one student said, well, yeah, but at least we know this really well now.
And
So
how many attempts did they make before they discovered the asymptotic medium?
Oh God, I don't know.
2 hours.
Like 50.
Well, and so the other really so I don't know how many attempts. It was a lot.
What was
At
the
least-
time? What was the time that you were just typing in? I mean, how?
Yeah,
The last time
what was the
stamp.
time stamp?
Oh, it was 10 minutes. 10 minutes in that whole section.
10 minutes.
That was the whole
I
section.
discovered the.
Well, that was, yeah, so maybe more like 8. I mean, it didn't take them long to get it to the top in 4 and 5 seconds, and then they just kept
Spent
trying.
most of their time trying to get it to go.
Yeah. And one interesting thing, if you look at it, is look at the intervals that they're shooting. So they got it to reach the top in 5 seconds at 225 meters per second. And then they think like, oh, well, I'll try 400 or something. And then they think, okay, 600. I mean, like it, so I don't think, and I probably would have done the same thing, but there's no intuition about like what's the scale I need to actually be shooting at. I mean, like they were at 20,000, still getting to the top in 5 seconds, and he thought, oh, well, surely it's less than 60,000. Well, you're already 2 orders of magnitude higher than 225, So, I mean, there's a lot of intuition building I think that you could do in using this sim. So another piece of data that I collected was a class survey. So in the spring, I had 27 students fill it out. I had 32 this semester fill it out. Same 1 to 5 scale, 5's the strongest, and same exact survey. So no differences at all. The first question here is the FET problem from last week helped me understand quadratic drag better. Okay, and so in both semesters we got basically the same average result, which is pretty neutral, 3.3 and 3.4. The second question was the FET sim provided me a helpful visualization for the problem last week. So slightly higher response, Yeah, so we had a 4.3 and a 4.0 here. They're really similar. And the last question is that the sim helped me make sense of my mathematical solution for V of t. And this is the lowest scoring question, and they're just about neutral. So I've got a little bit more survey data, but I didn't throw it in here either, where they kind of explain this a little bit, and I think most students didn't feel like the sim helped them to do the math, which obviously didn't help them solve the differential
I
equation.
wonder if their interpretation of neutral is it didn't help me, or disagree is an interpretation of saying it didn't help me.
Yeah.
Hard to know.
Yeah.
Certainly didn't help.
So Danny, I mean, you used your own heuristics presumably to modify from nothing to green to red.
Right.
You're developing heuristics. Would you say that the heuristics that you're developing were designed to try to improve the scores on this survey? Or were your heuristics designed for some other purpose and the survey is peripheral?
So it would have been nice if the survey would have had higher scores after this modification, but I don't think that's what I was really looking for. I was more interested in watching what the students did, because I felt like that was more indicative of what the question actually benefits or affords you, I guess. And the reason for that, I think, is because when they're working on it in that environment where I'm there and I kind of have a say in what they start working on. That's totally different than if they're working at home alone. And so, even when we did it, we didn't get, a lot of people just didn't do the problem. So I don't know. I don't know if I was expecting higher scores, but I wanted to give them a survey just to have that data.
I'm not sensitive to time, so if you could just
Okay.
wrap up,
Yeah. So the sim was not the main time consumer, but math was. The social setting, I think had a lot of benefits for the students who were there. So we did see instances of play and experimentation, and the students' reactions were also pretty interesting. They felt like they were wasting time, but also learning a lot. And the whole class overall was fairly neutral. That's a brief summary.
They felt they were learning a lot. They felt they were wasting time. So does that mean by the transitive property that learning is wasting time?
Yes. So it's just the only reason I point that out is because it's
wasting time, which is a really important lesson.
So it's not
Learning is not efficient.
Learning is not efficient.
So there were benefits with playing with the sim. I don't think they would have gained that same kind of intuition about what happens. On the other hand, playing with the sim to them felt like a waste of time because they had other work to be doing. So some of the heuristics I feel like could be drawn are, again, set up this game-like situation, or maybe, we've talked about maybe a better word is explicit challenges. So that's kind of open for discussion. Using the sim to mediate discussion again, and coordinating other forms of representation. In this case, it was math, trying to coordinate your solution for V of t with what you see on the sim. And we also utilize illuminating cases. In this case, the real illuminating case is the asymptote. And, this was kind of combined in this game-like situation or explicit challenge situation. And so one thing I'm starting to kind of wonder is maybe these two are sort of inseparable. Maybe you have to implement this as a game-like challenge. So I think those are kind of closely related somehow. But yeah,
All right.